All right, we're going all the way back in time, and watch this. We're going to like a 1980s elevator or something. I don't even know. It's so old. But all I know is we got some pretty smart scientists in there, so let's check it out real quick. All right, y'all, introduce yourselves. Come on.
Hello, I'm Mr. Briggs.
Come on, all right.
I'm Mr. Rauscher. I was part of this reaction with Mr. Briggs, who first created it in 1972.
All right.
In our experiment, we stirred the solution with a stirring rod instead of a magnetic stirrer, but the result should be roughly the same. Without stirring, the reaction will not be spatially uniform, instead going from top to bottom, as shown in the video.
To better understand the reaction, we need to know what causes each color. The original solution was created from 3 different solutions. One was potassium iodate and sulfuric acid, one was malonic acid, manganese sulfate, monohydrate, and starch, and one was just hydrogen peroxide. In order for the solutions to have specific colors, the electrons within the solutions must receive enough energy from incoming photons to move up a full energy level, and then release the absorbed energy as light because of atomic instability. The electrons have a minimum amount of energy they can absorb to move up an energy level, and that minimum energy dictates the frequency of light emitted by the solutions. The original solutions are all transparent when dissolved in water because the electrons within the solutions do not have enough energy to move up a complete energy level. The solution is not translucent because it is in the liquid state. It is a homogeneous surface that doesn't allow for the scattering of light. These solutions are dielectric, which means they are held together by ionic bonds. Unlike metals, which have a regular lattice structure and a sea of electrons, ionic compounds do not have free electron conduction. Because these solutions have a large amount of hydrogen bonding, the energy required to raise an electron to a higher energy is too high for the visible spectrum of light, making the solutions transparent. The resultant amber color is from the iodine in the solution. When dissolved in weakly polar solvents, the iodine turns brown. While the exact cause for the color is not known, it is suspected to be the energy absorbed and released by the iodine molecule in its partially ionized state. When photons hit iodine, they raise the energy level of its electrons, which then lower, releasing a brownish yellow light. The solution turns a deep blue color because of the triiodide. As the iodide concentration increases in the solution, iodide ions react with hypoiodous acid in the solution to produce diiodide, which then reacts with more iodide ions to produce triiodide. Explaining the color of triiodide is much more simple. It reacts very quickly with starch, forming a polyiodide homopolymer. It is extremely absorbent, releasing only a deep blue. The energy required to increase the energy level of the electrons is very small because of the increased charge. The starch iodine absorbs most low wavelengths of visible light, making the resulting color a deep blue. In our experiment, we saw oscillations between a colorless and amber solution, but not a deep blue one. This is because of excess chloride ion concentrations in the solution from not using distilled water. From an article published in 1975, we discovered that a concentration of chlorine above 0.07 m would suppress the oscillations, but no reason was given. We supposed that side reaction involving free chloride ions, both with the starch and the triiodine, can block triiodine from reacting with the starch and suppress the dark blue state of the system.
While it explains why we see each color, it doesn't explain why the solution oscillates between them. Here is the complete reaction with the intermediate steps. In the beginning, when all solutions were mixed, there was a low amount of iodine. Reaction 1 has 2 mechanisms, a radical and a non-radical process. A radical process is one that requires an atom or molecule that has an unbonded valence electron. In the beginning, the radical process is the reaction mechanism for reaction 1. It is important to note that even though the reactions are listed in order, they all occur simultaneously. That is not to say that they happen at the same speed. The radical process is much faster. All that means is that the radical process is able to create hypoiodous acid much more quickly than being consumed in the non-radical reaction.
As for why the radical process is faster is a more complicated matter. We're sure that many of you have noticed that reactions 1A1 and 1A2 are autocatalytic. For each HiO2 they consume, they produce 2. For IO2 to be reduced into HiO2, a manganese catalyst is required. At first, it is oxidized and then reduced, allowing for a more efficient pathway for the IO2.
With an excess of hypoiodous acid, hydrogen peroxide is able to bond with HIO to create iodine. The iodine is able to react with more HIO to create iodide, which is responsible for the yellow color. As the reaction continues, more and more iodide is created, which eventually reacts with iodine to create triiodide. The triiodide reacts extremely quickly with the starch indicator, turning the entire solution deep blue.
The reaction did not occur any sooner because there was always excess HIO that could bond with iodine. It was only when the concentration of HIO was less than iodine that it was able to bond with iodide to create triiodide. This is because of the charge on the iodine are negatively charged, meaning that they have an extra electron. Iodine bonds with HIO, a very, very slightly polar acid, when given the chance. It is very strange that iodide would form another molecule, as the octet appears to be full and stable, but it makes sense if you remember that the Lewis dot structure is simply a model. If you imagine a different shape, such as a 4-electron 3-center bond, triiodide is in fact more favorable than iodide. The negative charge is spread out over a greater number of atoms, making it more stable. The starch indicator, in our case a laboratory-grade potato, has a significant amount of amylose, a long molecule that is created with glycosidic bonds. Its unique shape makes it incredibly important in nutrition, but its shape also makes it very useful in chemistry. Amylose is a parallel double helix, creating a structure that is very similar to that of a spring.
When the concentration of iodine is high enough, the non-radical process is more significant in the reaction. Now that the first reaction is slower than the second one, more iodine is consumed than produced. Finally, the solution reaches similar initial conditions, repeating the process until the malonic acid, or iodate, is consumed.